It is 280 million years after the beginning of everything. The universe is not yet 2% of its current age. There are no planets, no solar systems, no human eyes to observe any of it. And yet, there is a galaxy, a real, burning, chemically complex, star-forming galaxy already blazing in the dark, roughly 500 light-years across, generating more ultraviolet radiation than anything we know how to explain. It should not be there. Every model we built, every prediction we calculated, every simulation we ran, all of them agree. And all of them are wrong. This is the story of what the James Webb Space Telescope found at the very edge of time. And I want to warn you up front, the answer it gave us did not close a question. It detonated one. Before we can understand what was found, we need to understand what it took to find it. Because the James Webb Space Telescope is not merely a better version of what came before. It is a category of instrument that did not previously exist on Earth, or above it. Hubble, for all its revolutionary contributions to human knowledge, was a telescope built for a particular era of the cosmos. Its mirror, 4 meters across, was a precision marvel when it launched in 1990, and it spent 3.5 decades reshaping our understanding of the universe's age, scale, and content. But Hubble was ultimately constrained by physics it could not overcome: the light from the very earliest galaxies. Objects formed within the first few 100 million years of cosmic history arrives at our instruments so severely stretched by the expansion of space that it no longer appears as visible light at all. It has been pulled wavelength by wavelength into the infrared, and Hubble, for all its greatness, was not primarily built to see in the infrared. Webb was. The James Webb Space Telescope, a joint program led by NASA with ESA and the Canadian Space Agency, launched on Christmas Day 2021. Its mirror stretches 5 meters across, a surface area almost 7 times that of Hubble's, composed of 18 hexagonal beryllium segments, coated in a layer of gold so thin that if you stretched it out to the thickness of a standard page of printer paper, the gold would disappear entirely. It was positioned at the second Lagrange point, 1.5 million kilometers from Earth, behind a 5-layer sunshield the size of a tennis court, designed to cool its infrared detectors to a temperature of -233 degrees Celsius, within 40 degrees of absolute zero. All of this engineering had a single purpose: to see the light of the very first galaxies in a universe that had just been born. Before Webb launched, astronomers were cautiously optimistic about what it might find in the deep early universe. Theoretical models, built on decades of cosmological observation and refined through increasingly powerful computational simulations, predicted that the first few 100 million years of cosmic history would yield galaxies that were small, faint, and rare. Finding even a handful of confirmed objects at what astronomers call a redshift above 10, objects from a time when the universe was less than 500 million years old, would have been considered a triumph. Most models predicted Webb would need tens of hours of observation per target to detect anything meaningful at that distance. The universe, it was assumed, had not had time to build anything impressive yet. Within the first weeks of science operations, Webb began to suggest that this picture was not just incomplete. It was, in some fundamental and disquieting way, incorrect. To appreciate what Webb found, you first need to understand what the universe looked like in those first few 100 million years, and why astronomers expected it to look the way they predicted. The Big Bang, approximately 8 billion years ago, produced a universe of pure energy. As that energy cooled over the first few minutes, it condensed into the lightest elements: hydrogen, helium, and trace amounts of lithium. For the first 370,000 years, the universe was so hot and so densely packed that light could not travel freely through it. Every photon emitted was immediately absorbed and re-emitted by the surrounding plasma. The universe was opaque, a glowing, dense fog of charged particles. Then, as the temperature dropped below about 3000 Kelvin, electrons and protons combined for the first time into neutral hydrogen atoms. The fog cleared. Light travelled freely for the first time. This moment is called recombination, and it is the source of the cosmic microwave background, the faint afterglow of the Big Bang that we can still detect in every direction today. But then something strange happened. The universe went dark for a period lasting tens of millions of years. Astronomers call it the cosmic dark ages. There were no stars, no galaxies, no sources of light. Just hydrogen gas and dark matter slowly clumping under gravity into filaments and halos, building the scaffold of what would eventually become the cosmic web. This was the universe in its most patient form, assembling itself in total darkness, gravity doing its slow work, concentrations of matter growing denser by fractions over millions of years. Then, somewhere in that darkness, the first star ignited. We have never directly observed this moment, but we know it happened, because the evidence of what came after is written across the entire history of the cosmos. These first stars, called population 3 stars, are predicted to have been monsters by modern standards, objects potentially thousands of times the mass of our Sun, burning with a ferocity no star alive today can match, and living for perhaps only 1 million years before exploding as supernovae. They seeded the universe with the first heavy elements: carbon, oxygen, nitrogen, elements heavier than helium that did not exist in the Big Bang's first moments. And they produced the first light energetic enough to strip electrons from the surrounding hydrogen gas. This process, ultraviolet light from the first stars ionizing the neutral hydrogen fog that filled the universe, is called the epoch of ionization. It is, in some respects, the second most dramatic transformation in the history of the universe. The moment when the cosmos woke up from its dark childhood and became the transparent, star-filled place we inhabit today. Reionization is thought to have begun somewhere around 400 million years after the Big Bang and concluded roughly 1 billion years in, by which point the hydrogen between galaxies had been fully stripped of its electrons. But here is what the models predicted about the objects responsible for doing the stripping. They would be small, they would be dim, they would be building blocks, galactic embryos, not adults. A galaxy at 300 million years after the Big Bang, by the pre-Webb consensus, should resemble the seed of what would eventually grow into a Milky Way. Not anything approaching the mature, chemically complex, star-producing systems we see in the universe today. This prediction was built on something called hierarchical structure formation, the bedrock principle of modern cosmology. The idea, supported by decades of observation and by the extraordinary success of the lambda cold dark matter model, is that structure in the universe builds from the bottom up. Small things form first. Small things merge into bigger things. Big things, galaxies, galaxy clusters, the filaments of the cosmic web, take time, lots of time, are the product of billions of years of accumulated merging, accretion, and stellar evolution. This is how we thought the early universe worked. And this is what Webb, within months of switching on its instruments, began to challenge in a way that no one had anticipated. The first hint came not from a single startling discovery, but from a pattern. Webb began returning images of the deep universe, and the astronomers analysing them, including teams from the Sears Survey, the GLASS program, and UN Cover collaboration, began noticing the same thing independently. There were too many bright galaxies at too great a distance. Not slightly too many, not a marginal statistical anomaly that could be explained away by measurement uncertainty or calibration error. The excess was a factor of roughly 100 above what the models had predicted, 100 times more luminous early galaxies than anyone expected to find. That number, 100 times, deserves to sit in the open air for a moment because it is not a rounding difference. A factor of 100 in science is not a footnote. It is a foundational mismatch. This is what physicists call the bright galaxy abundance problem, and it was the opening act of something even more confounding that Webb was about to deliver. When the first wave of Webb's deep field results began circulating in preprint form in late 2022, the immediate popular interpretation, enthusiastically amplified across the internet, was that Webb had broken cosmology. Headline after headline declared that these early galaxies were too big, too bright, and too mature to be reconciled with the standard model of the universe. Some went further, suggesting that the Big Bang itself might need to be reconsidered. This was, to put it charitably, an overstatement. But the underlying problem was real, and it was serious enough to occupy some of the most talented observational cosmologists in the world for the next 3 years. To understand why, you need to understand what the standard model, formerly known as lambda cold dark matter, or LCDM, actually predicts about the early universe, and precisely which aspects of it Webb's findings were straining. The LCDM model is one of the most precisely tested frameworks in all of science. It describes a universe dominated by 2 unseen components: lambda, representing dark energy, the mysterious force accelerating the universe's expansion, and cold dark matter, the invisible gravitational scaffolding within which ordinary matter, stars, gas, planets, assembles itself. Within this model, the universe's history is extraordinarily well constrained. We know the age of the cosmos to within 20 million years. We know the precise ratios of ordinary matter, and dark energy. We know the geometry of space-time to extraordinary precision from measurements of the cosmic microwave background. What the model does not directly specify, what has always required separate physical submodels sitting on top of the cosmological framework, is the process of galaxy formation itself. How quickly does gas cool inside dark matter halos? What triggers the collapse of gas clouds into stars? How efficient is that process? How does radiation and supernova feedback regulate and sometimes completely halt star formation? These are galaxy formation physics questions, not cosmological ones, and they are far harder to model precisely. The problem with the earliest Webb galaxies was that even the most generous galaxy formation models had difficulty accommodating them. The argument goes roughly as follows. In the LCDM framework, dark matter halos of a given mass are expected to be present in certain numbers at certain times. The most massive halos form last, because small halos merge over time into larger ones. At 300 million years after the Big Bang, the very largest halos available are themselves limited in size, and the efficiency with which gas inside them converts to stars is capped by fundamental physical constraints, the Eddington limit being one of the most ironclad. A galaxy cannot form stars faster than a certain rate without the radiation pressure from those stars blowing the gas cloud apart before the collapse completes. So when Webb started finding galaxies that were not only more numerous but also more luminous than expected, the question became, what is driving the brightness? There are, it turns out, 4 possible answers, and astronomers have been working through them with the methodical intensity of scientists who know the stakes. The first possibility is that Webb itself is simply better than expected. The telescope was manufactured to tighter tolerances than its conservative pre-launch specifications, and its mirror gathered more light than the guaranteed minimum. This effect is real, it matters, but by itself, it does not come close to explaining a 100-fold excess. The second possibility concerns simulation resolution. Most galaxy formation simulations are conducted at medium resolution across large volumes, which means they smooth over the rarest and most extreme small-scale overdensities in the early universe. When these extreme environments, regions of space where dark matter density was unusually high at very early times, are included more carefully, more bright early galaxies emerge naturally from the models. This is also a real effect, and it closes part of the gap. The third and perhaps most physically compelling possibility is what astronomers call bursty star formation. Instead of galaxies building their stellar populations at a steady, gradual rate, they may instead form stars in violent episodes, brief, intense bursts during which star formation rates temporarily spike far above their long-term average. During such a burst, a relatively small galaxy can appear momentarily as luminous as a much larger one, and because Webb preferentially detects the brightest objects at any given time, the population it observes would be biased toward catching galaxies in their brightest moments. This effect is now thought to be one of the dominant explanations for the observed excess. The fourth possibility involves active galactic nuclei, supermassive black holes at galaxy centers that are actively accreting material and radiating energy in quantities that can temporarily outshine the entire stellar population of their host galaxy. Many of the early Webb galaxies show signatures consistent with AGN activity. If a significant fraction of their luminosity comes from a feeding black hole rather than newly formed stars, then the implied stellar masses, and hence the challenge to Lie CDM, are considerably smaller than initially feared. By 2024, with all four effects carefully weighed, the consensus in the community had shifted. The early Webb galaxies were not breaking cosmology. The standard model was, with some strain and considerable head-scratching, surviving. But here is what makes the story richer and more troubling than a simple resolution. Just as this accommodation was being reached, Webb delivered two objects that refused to accommodate themselves to any explanation then in hand. The first was JWST 14.0. The second was something even more distant, and together they represent what Rohan Naidu of MIT's Kavli Institute, the lead author of the discovery paper for the second, called, in the title of his published paper, without any apparent irony, a cosmic miracle. The JWST Advanced Deep Extragalactic Survey, abbreviated JDES, was designed from the beginning for a particular kind of audacity. Combining the observational power of two of Webb's primary scientific instruments, NIRCam and NIRSpec, the JDES program targeted some of the richest regions of the deep sky, staring for hundreds of cumulative hours into patches of the universe so remote that the light arriving at the detector had been travelling since before our solar system existed. The team behind JDES is a collaboration of European and American astronomers, led in part by Stefano Carniani of the Scuola Normale Superiore in Pisa, Italy, and Daniel Eisenstein of Harvard. It is a program built not for quick answers, but for the slow, painstaking accumulation of precise knowledge about the farthest reaches of observable time. In January 2024, the NIRSpec instrument, Webb's extraordinarily sensitive near-infrared spectrograph, capable of dispersing the light from a galaxy into its component wavelengths and reading the chemical fingerprints encoded within, was pointed at a candidate galaxy that had been flagged during earlier imaging passes. The object was small, it was distant. The photometric redshift estimate, a preliminary measurement derived from how the galaxy's colour changed across different infrared filters, suggested it was ancient, but photometric estimates can be wrong. What the team needed was a spectrum, a definitive measurement. NIRSpec observed the object for nearly 10 hours. When the spectrum was first processed, there was a moment, described by several team members in subsequent interviews, of something very close to disbelief. The data revealed a sharp, clean break in the spectrum precisely at the wavelength predicted by the Lyman alpha transition, the spectral signature of neutral hydrogen absorbing ultraviolet light. This is the key tool astronomers use to measure cosmic distance. The wavelength of the break shifted from its rest frame value of 121.5 nanometers to an observed wavelength deep in the infrared, told the team exactly how much the universe had expanded since this galaxy's light was emitted. The answer translated to a redshift of 1432. This placed the galaxy at a time when the universe was approximately 290 million years old, less than 2.2% of its current age. It was the most distant confirmed galaxy in human history. By a significant margin, the object was named JWST 14.0, and it appeared in the constellation Fornax. Its light travel time, the time it took for its photons to cross the expanding universe and arrive at Webb's mirror, was approximately 13.5 billion years. In that time, the Earth formed and died twice over in terms of geological epochs. Every civilization in human history rose and fell, and rose again countless times. And this galaxy had been sitting there, its ancient light racing toward a telescope that would not be built for another 13.499 billion years. But JWST 14.0 was not merely historically significant, it was deeply structurally strange, and the strangeness emerged in layers, each more unsettling than the last. The galaxy is 1,600 light-years across. This is not enormous by modern standards. Our own Milky Way stretches roughly 100 zillion light-years in diameter, but 1,600 light-years is substantial for an object supposedly at the very first gasp of galaxy formation. More striking than the size was the luminosity. JWST 14G is extraordinarily bright in ultraviolet light, implying a star formation rate far beyond what standard models predict for an object of this age. The galaxy appears to contain hundreds of millions of solar masses worth of stars. Already, the universe was 290 million years old. There simply had not been time, under conventional galaxy formation timescales, for this much stellar material to accumulate. But the most confrontational finding came later, in 2025, when two independent teams of astronomers turned the Atacama Large Millimeter SOP Millimeter Array, ALMA, the world's most powerful radio telescope, perched at an altitude of 5,000 meters in the Chilean desert, toward JWST 14-0. They were looking for emission from ionized oxygen, a spectral line at a wavelength of 88 microns that serves as a reliable tracer of chemically enriched gas. Oxygen is a heavy element. It is not produced in the Big Bang. Oxygen exists in the universe only because stars lived and died, fusing hydrogen and helium in their cores over millions of years, and then exploding as supernovae, scattering their nuclear products into the interstellar medium. For oxygen to exist in a galaxy, that galaxy must have already hosted at least one complete generation of stellar evolution. Both teams detected the oxygen, independently, unambiguously. JWST 14-0, at 290 million years after the Big Bang, contained approximately 10 times more oxygen, 10 times more chemical enrichment, than any reasonable model of early galaxy evolution had predicted for an object this young. The lead author of one of the studies, Sander Schaus of Leiden Observatory, described the finding with an analogy that I think captures its essence perfectly. It is, he said, like finding an adolescent where you would only expect babies. And Stefano Carniani, leading the second team, put it with the precision of a scientist who has had time to absorb the shock. The evidence that a galaxy is already mature in the infant universe raises questions about when and how galaxies formed. This is what I find genuinely staggering about JWST 14-0. Not the distance, extraordinary as that is, not the luminosity, but the oxygen, because oxygen is, in a very real sense, cosmic biography. Every atom of it in that galaxy represents a star that lived and died before the universe was 290 million years old. We are not looking at a first-generation object. We are looking at a galaxy already in at least its second chapter, with the ashes of dead stars woven into its interstellar medium. Something happened in the universe's very first moments that we do not yet understand. Something that allowed star formation to proceed so rapidly, so efficiently, and on such a scale that an entire generation of stars had already lived and died, while the universe was still what most cosmologists would call an infant. And then, in May 2025, Webb broke its own record. There is a particular kind of intellectual courage required to ask a question you genuinely do not know the answer to, especially when the answer might be, our entire framework is wrong. Rohan Naidu is an astrophysicist and postdoctoral researcher at MIT's Kavli Institute for Astrophysics and Space Research in Cambridge, Massachusetts. He is, by the accounts of colleagues, the kind of scientist who approaches the edge of the known not with caution, but with the urgency of someone who suspects the edge is closer than advertised. In the years following Webb's first light, Naidu had been part of the community wrestling with the same question that everyone was wrestling with. Were the bright early galaxies Webb was finding real, or were they mirages, photometric artifacts, misidentified foreground objects, tricks of the data? The question was not merely academic. If the abundances were real, if the universe genuinely hosted something like 100 times more luminous early galaxies than the models predicted, then something fundamental was missing from the standard picture of how the cosmos assembled itself. If they were mirages, then the models were safe, and Webb's contribution was to sharpen the boundaries of an already solid paradigm rather than rupture it. Naidu designed a survey to find out. He called it the Mirage or Miracle Survey MOM, and the name carries within it the full weight of the question. Together with Pascal Oesch of the University of Geneva, co-principal investigator, and a team of 45 scientists spanning institutions across Europe, North America and Japan, Naidu constructed a program to systematically target the most luminous high redshift galaxy candidates in the Cosmos Legacy Field, one of the most deeply studied regions of the sky, and confirm or refute them with Webb's NIRSpec spectrograph. Every pointing received 4.4 hours of integration in the prism mode. The goal was clarity. Take the photometric candidates and either collapse them into confirmed objects with precise redshifts and spectroscopic properties, or expose them as contamination. Naidu had spent months building the target list. The Cosmos field had been imaged by an array of JWST programs, Cosweb, Primer, Bluejay, Panoramic, and others, generating a photometric catalogue of hundreds of candidate objects at redshifts above 10. The MOM survey was designed to systematically attack the brightest end of this distribution, the objects that, if confirmed, would pose the greatest challenge to theory. These were not the safe targets. These were the ones that, if real, would be the hardest to explain. On the 16th of April 2025, the NIRSpec instrument aboard the James Webb Space Telescope observed one of these targets. The object had been sitting in the photometric catalogue for some time, flagged as a candidate on the basis of its infrared colours. In the imaging data, it was compact and entirely absent below wavelengths of about 2 microns, a signature consistent with the Lyman alpha break of a very distant galaxy. But photometry is not certainty. Photometry is a hypothesis. The spectrum would decide when the spectroscopic data came back and the team processed it, using version 0.9.4 of the MSAX software, a reduction pipeline built specifically for Webb NIRSpec data. Naidu saw a sharp, clean break in the continuum consistent with Lyman alpha absorption. But unlike most confirmations at high redshift, which are made on the basis of this single feature alone, the spectrum of this object showed something more. 5 separate emission lines, nitrogen, carbon, and others, each independently placing the galaxy at the same distance. 5 independent votes, all pointing to the same answer. The redshift was 1444, plus or minus 0.02. This placed the object at a time when the universe was approximately 280 million years old, 10 million years earlier in cosmic history than JWST Z14-0, the most distant confirmed galaxy in the history of human civilization. The team named it MOM-Z14, and a paper was submitted to the Open Journal of Astrophysics. The confirmation was made public on the 16th May 2025, exactly 1 month after the observation. What I find humanly compelling about this moment is the specific shape of what Naidu said when the data came back confirmed. Not triumphalism, not the breathless excitement of a record broken. What he said to NASA for public release was this: with Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. The acknowledgement comes first, the thrill comes second. That ordering, I think, tells you something important about the quality of mind required to do this kind of science honestly. Because the honest answer here is not comfortable, and the people doing this work are not comfortable with comfortable answers. Jacob Shen, a postdoctoral researcher at MIT and a member of the research team, described the situation with similar directness. There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. A growing chasm, not a bump, not a tension. A chasm. Yijia Li, a graduate student at Pennsylvania State University and team member, struck perhaps the most genuinely open to scientific note. To figure out what is going on in the early universe, we really need more information, more detailed observations with Webb, and more galaxies to see where the common features are. Not a revolution, not a paradigm collapse, more information. This is science doing what science does at its best, remaining honestly uncertain and building the next question on the best available answer. What the survey also confirmed with a statistical punch that makes the discomfort unavoidable, is that the abundance of galaxies at the cosmic frontier is not a mirage. MOMZ14 is real. The number density of bright galaxies at redshifts of 14 to 15, implied by finding one object in MOM's survey area of approximately 350 square arc-minutes, is more than 100 times higher, in one statistical estimate 182 times higher than pre-JWST theoretical consensus had predicted. The miracle is not a single galaxy, the miracle is the count, and it has not yet been explained. Let us stand in front of MOMZ14 and look at it carefully, because what it is, as an object, is as confrontational as the fact of its existence. It is compact. The effective radius of MOMZ14 is measured at 74 parsecs, approximately 241 light-years. For comparison, the Milky Way's disk extends roughly 50,000 light-years from its centre in each direction. The entire galaxy of MOMZ14 would sit comfortably within a single arm of our galaxy with room to spare. Its total diameter, accounting for extended emission, is approximately 500 light-years. It is smaller than many of the individual star-forming nebulae within the Milky Way, and yet, within those 500 light-years, something extraordinary is happening. The galaxy has a mass of approximately 100 million solar masses, comparable to the Small Magellanic Cloud, one of the Milky Way's dwarf satellite galaxies. But the Small Magellanic Cloud has been building that mass for over 10 billion years. MOMZ14 had 280 million years. It has accomplished in less than 3% of that time frame what took the SMC its entire existence. The star formation rate inside MOMZ14 increased by a factor of approximately 10 in the last 5 million years before the epoch we observe it. Something switched on in this galaxy with extraordinary abruptness and efficiency. It is almost entirely free of dust. The ultraviolet slope of its light, measured as a spectral index of -2.5, is steep and blue, which in astrophysical terms means the light is unimpeded by the dust grains that normally form in older, more evolved stellar populations. Dust requires heavy elements. Heavy elements require dead stars. The near absence of dust in MOMZ14 is consistent with a very young stellar population, and yet, paradoxically, the emission lines in its spectrum tell a different story. Those emission lines reveal something that has become a recurring, disturbing motif in the study of the earliest JW galaxies, nitrogen. Specifically, MOMZ14 shows an extremely high nitrogen-to-carbon ratio. The ratio of NC in MOMZ14 is greater than 1, a value that in the standard chemical enrichment framework requires the presence of stars massive enough and hot enough to produce and disperse unusual amounts of nitrogen. In the nearby universe, this kind of nitrogen enrichment is associated almost exclusively with one specific class of objects: globular clusters, dense, ancient balls of stars that orbit our galaxy and others, some of them nearly as old as the universe itself. And within globular clusters, a subset of their oldest, most chemically peculiar stars shows exactly this high nitrogen signature. These are called multiple stellar populations, and their origin has been one of the most vexing puzzles in stellar astrophysics for decades. The connection the MOM team draws, and it is a remarkable one, is this: the ancient nitrogen-enriched stars in the Milky Way's globular clusters may be the surviving descendants of galaxies exactly like MOMZ14. What we are witnessing, when we look at this object 280 million years after the Big Bang, may be the formation of the precursor population to the oldest stars in our own galaxy. We are not merely observing a distant and alien object. We may be watching, in real time, the birth of structures that still exist today in the halos of galaxies like the Milky Way, ancient, preserved, carrying chemical fingerprints set down in the first few 100 million years of cosmic history. One theory to explain the nitrogen signature is the most extraordinary of all: supermassive stars. Not the kind of massive stars we observe today, objects like R136A1, the most massive known star in the Milky Way, at approximately 200 to 300 solar masses. These hypothetical objects would be on an altogether different scale, thousands to tens of thousands of solar masses, burning at temperatures and luminosities that almost defy calculation. Such stars, if they existed in the dense, gas-rich environments of the early universe, could have produced the chemical enrichment signatures we observe in MOMZ-14 in a fraction of the time conventional stellar evolution would require. They are sometimes called population 3 stars in their most extreme incarnations, though theorists are careful to distinguish between the modest hypergiants, sometimes called POP3, and these truly monstrous hypothetical objects. We have never observed a supermassive star. We have theoretical reasons to believe they may have existed in the universe's first few 100 million years, when gas could collapse under gravity without the disruptive feedback mechanisms that limit stellar masses in the metal-enriched environments of today. If MOMZ-14 hosted objects in this mass range, it would explain the nitrogen, it would explain the luminosity, it might even explain why this galaxy appears so chemically mature despite its youth. But here is the layer of the problem that this explanation does not resolve, and that I find genuinely haunting. MOMZ-14 shows essentially no absorption from the surrounding neutral hydrogen that should, according to every model of reionization, be nearly everywhere at this epoch. The universe at redshift 14.44, 280 million years after the Big Bang, should be almost entirely opaque in the hydrogen ionizing ultraviolet, because reionization had barely begun. The intergalactic medium should be a near-complete fog of neutral hydrogen, and yet the light from MOMZ-14 does not show the damping wing absorption pattern that a fully neutral hydrogen fog would produce. The immediate surroundings of MOMZ-14 appear to be partially ionized already. This means one of two things. Either MOMZ-14 is itself, by some extraordinary physical mechanism, managing to ionize an enormous bubble of intergalactic hydrogen around itself hundreds of millions of years earlier than reionization models predict, burning through the fog with a ferocity we cannot yet account for, or the neutral hydrogen fraction of the intergalactic medium at this location and this epoch is dramatically lower than any reionization model predicts it should be. Neither answer is comfortable. Both demand explanation. Both push directly against what we thought we understood about one of the most important phases of cosmic history. This is the structure of the problem as it currently stands. An object that is too bright, too chemically enriched, too numerous, and located in a region of space that is too transparent, at a time when the universe should be none of these things. And it is not alone. The phrase growing chasm that Jacob Shen used to describe the gap between theoretical predictions and Webb's observations deserves to be taken seriously, not as hyperbole, but as a precise technical description of the state of the field. Before JWST began science operations, the theoretical consensus for the early universe rested on several interlocking pillars. First, hierarchical structure formation. The universe builds from the bottom up, with small structures forming first and merging into larger ones over time. Second, star formation efficiency. The fraction of gas in a dark matter halo that actually collapses into stars is limited by a combination of gravity, radiation pressure, and supernova feedback, and this efficiency is expected to be modest, typically a few percent, in the early universe. Third, the timeline of reionization. The neutral hydrogen epoch is expected to be essentially complete above redshift 6, meaning that by 1 billion years after the Big Bang, the universe is transparent. But below redshift 6, at earlier times, the universe should be increasingly opaque, with the neutral fraction approaching 100% by a redshift of around 12 or 13. Webb has not yet broken any of these pillars outright, but it has applied stress to each of them in ways that the community is working urgently to resolve. The bright galaxy abundance problem, the factor of 100 excess in the number of luminous early galaxies, is the most statistically robust challenge. As described in the previous chapter, 4 partial explanations exist: JWST's optical performance exceeding conservative pre-launch specs, improved treatment of rare peak overdensities in simulations, bursty star formation temporarily inflating observed luminosities, and AGN contributions adding black hole-powered luminosity to stellar light. Together, these four effects bring the theoretical predictions considerably closer to the observations. For the majority of Webb's early galaxies, the combination is probably sufficient, but JD's GSZ14 JESH and MOMZ14 sit uncomfortably even with all four corrections applied. The paper by Naidu and colleagues, the MOM discovery paper, reports that even with these explanations on the table, the number density of bright galaxies at redshifts 14 to 15 implied by their survey is between 77 and 511 times larger than pre-JWST consensus models predict, with a best estimate factor of 182. This is not within the uncertainty of a model that has been partially corrected. This is a residual discrepancy of historical proportions. There are researchers who argue that this residual can still be accommodated by pushing the galaxy formation models harder. If star formation efficiency in the very earliest objects was substantially higher than the models assume, driven perhaps by the absence of feedback mechanisms that suppress star formation in enriched environments, then brighter early galaxies are plausibly explained without revising fundamental cosmology. The argument goes that we simply underestimated the fraction of gas that collapses into stars in the universe's first few 100 million years. This is a model within the existing paradigm. It does not require new physics. But the chemical enrichment problem in JD's GSZ14 is harder to dismiss. 10 times more oxygen than expected, at a distance of 290 million years after the Big Bang, is not a model parameter that can be tuned with standard assumptions. Oxygen requires dead stars. Dead stars require complete stellar lifetimes. Even the most massive stars that we know of live for only a few million years. To have 10 times the expected oxygen abundance, JD's GSZ14 must have hosted not one but multiple rapid, efficient generations of massive stellar evolution, all completed within the first 290 million years. The timescale is tight, uncomfortably tight. The reionization problem presented by MOMZ14 adds a third strand to the challenge. Every quantitative model of reionization, and there are many built with increasing sophistication over the last 2 decades, agrees that the intergalactic medium at redshift 14.44 should be very nearly 100% neutral. The hydrogen fog should be essentially impenetrable, and yet MOMZ14's spectrum shows evidence that the space around it is partially ionized. The team notes, with notable understatement, that this is a redshift where virtually every reionization model predicts a 100% neutral fraction. One possible interpretation is that MOMZ14 represents an unusually active site of early reionization, a place where, by chance or by particular physical conditions, the process of hydrogen ionization began hundreds of millions of years earlier than average. Another is that the reionization timeline itself needs revision. A third is that there are sources of ionizing photons in the very early universe, perhaps those hypothetical supermassive stars, or perhaps something else entirely that the models do not account for. What makes all of this particularly scientifically productive is not the discomfort it causes, but the specificity of the discomfort. Webb is not generating vague anomalies that could mean anything. It is generating precise measurements, redshifts accurate to fractions of a percent, chemical abundances with well-characterized uncertainties, morphological measurements at sub-kiloparsec resolution that point to specific, testable tensions in specific identifiable parts of the theoretical framework. This is the machinery of science operating in its healthiest mode, not delivering answers but engineering better questions. There is one further aspect of JD's GSZ14 and MOMZ14 that I want to dwell on because I think it represents perhaps the deepest conceptual challenge embedded in these discoveries. It concerns identity, the question of what kind of objects these galaxies actually are, and what they are growing into. The nitrogen abundance pattern in MOMZ14, echoing what was found earlier in GNZ11, the third most distant confirmed galaxy, now confirmed at redshift 10.6, is specifically similar to the chemical fingerprints found in the ancient stars of the Milky Way's globular cluster population. Globular clusters are extraordinary objects. spherical collections of hundreds of thousands to millions of stars, gravitationally bound, orbiting large galaxies in their halos. The Milky Way has approximately 150 of them. They are among the oldest structures in the universe, and some of their stars carry chemical signatures, including this high nitrogen to oxygen pattern that have never been fully explained and that were present from the very early universe. What Naidu's team is suggesting is that objects like MOMZ-14 may be protoglobular clusters, the direct ancestors of those ancient stellar cities that still orbit the Milky Way today. The compact sizes, the bursty star formation, the unusual chemical abundances, all of these are consistent with an object that will not become a Milky Way-like spiral galaxy, but instead a dense, ancient globular cluster, eventually captured by a larger galaxy and incorporated into its halo, carrying for the next 13 billion years the chemical memory of its birth in the universe's first few 100 million years. If this interpretation is correct, and it is speculative, let it be said, then the oldest structures we can observe in the Milky Way today are the survivors of exactly the kind of cosmic epoch that Webb is now photographing at the limits of the observable universe. The light arriving at the James Webb Space Telescope from AOMZ-14 may be showing us the birth of objects whose descendants still orbit us, close enough to study with ground-based telescopes. The universe's deep past and its observable present are joined by a continuous thread. This is, to my mind, one of the most breathtaking conceptual connections that modern astronomy has ever produced. The ancient stars in the Milky Way's globular clusters are not merely old. They may be the diaspora of galaxies exactly like the one Webb just found at the very edge of time. Here is what Webb has confirmed. As of mid-2026, the universe's earliest observable epoch is more active, more chemically complex and more structurally developed than anything the pre-Webb theoretical consensus predicted. Galaxies exist at 280 million years after the Big Bang that are already enriched with heavy elements, already forming stars at extraordinary rates, already partially ionizing their surroundings. Their abundance exceeds predictions by a factor that varies from roughly 100 to perhaps 200, depending on the precise redshift and survey area, and at least some of them show chemical signatures connecting them directly to the oldest surviving stellar structures in the present-day Milky Way. This is not a tidy conclusion. It is a precisely specified opening. The next phase of this investigation will unfold along several fronts simultaneously, and each of them carries the potential to either tighten the screws on the existing theoretical framework or release the pressure in an unexpected direction. The most immediate priority is exactly what Yijia Li described, or galaxies. MOMZ-14 was found in a survey area of approximately 350 square arc-minutes. This is equivalent to a patch of sky roughly half the angular size of the full moon. The observable universe is incomparably larger than that. To understand whether MOMZ-14 and JWST represent a statistical population or extreme outliers, astronomers need a sample. Not 2 objects, not 10, hundreds, ideally thousands, of confirmed spectroscopic redshifts at these extreme distances enter the Nancy Grace Roman Space Telescope. Construction of the Roman telescope was completed in November 2025, and it is currently scheduled to launch by May 2027. Named for NASA's first chief of astronomy, Roman represents what Webb cannot accomplish. A wide field of view 100 times larger than Hubble's, capable of surveying billions of galaxies across billions of light years in a fraction of the time it would take Webb to cover the same area. Where Webb can stare deeply into a small patch and find the most extreme individual objects, Roman can sweep across the sky and provide the statistical context that Webb's individual discoveries demand. The MOM team itself has noted explicitly that Roman will be able to boost the sample of bright, compact, chemically enriched early galaxies into the thousands. That transformation, from a handful of extraordinary individuals to a statistically robust population, is what will turn the current theoretical tension into a precisely measured, precisely challengeable claim. But Webb itself is far from finished. Follow-up observations of MZ14 with near-spec at higher spectral resolution, planned but not yet completed as of the time of writing, will probe the galaxy's chemistry in far greater detail, potentially resolving the nitrogen signature with sufficient precision to distinguish between the supermassive star hypothesis and alternative explanations. If supermassive stars are responsible for the chemical enrichment pattern, their spectral signatures should, in principle, be detectable. We have never identified a supermassive star in the universe. If Webb finds evidence for them in MZ14 or objects like it, that would represent a discovery of the first order, not merely a new kind of object, but a class of stellar object that existed only in the universe's earliest moments and has left no surviving representatives in the present day. ALMA 2 remains indispensable. The detection of oxygen in JWST was made with an uncertainty of just 0.005% in the galaxy's distance measurement, a precision analogous to being accurate within 5 centimeters over 1 kilometer. Future ALMA observations of MZ14 will search for the same oxygen signature at redshift 1444. If oxygen is detected there as well, the chemical enrichment problem deepens considerably. 2 confirmed objects at 2 different extreme distances, both showing an abundance of heavy elements that the models cannot explain without invoking either dramatically elevated star formation efficiency, exotic stellar populations, or some combination of both. The reionization question, the problem of why MZ14's surroundings appear partially ionized at a time when the universe should be essentially opaque, may prove the most theoretically revealing of all. This is because reionization is not a local phenomenon. It is a global phase transition of the entire intergalactic medium, driven by the cumulative ionizing radiation from all the early galaxies, and potentially from other sources. If early galaxies were present in the numbers Webb implies, and if they were producing ionizing photons at the rates the spectral data suggests, then reionization may have begun substantially earlier than the models predict. The constraint that reionization completed around 550 million years after the Big Bang derived from the spectra of distant quasars and from the cosmic microwave background polarization signal would not necessarily be violated by an earlier start date. Reionization could have begun earlier, proceeded more patchily, and lasted for a shorter period in some regions of the sky than others. MZ14 may be sitting inside just such an early ionized bubble, a local region where, for reasons of particular galaxy density and star formation activity, the hydrogen fog cleared hundreds of millions of years ahead of schedule. This would have an important implication. The earliest epochs of the universe were not uniformly dark, waiting for a single coordinated switch-on of stellar light. They were patchy, local, variable, a landscape of early ionized bubbles forming around the most active star-forming sites, while the surrounding intergalactic medium remained neutral for hundreds of millions of years longer. The epoch of reionization, rather than a clean phase transition, becomes more like a landscape of campfires, appearing one by one in the darkness, before the collective glow is sufficient to illuminate everything. There is a broader theoretical debate lurking behind all of this that I want to name directly, because it is the question that gives these individual discoveries their civilizational weight. The Lambda Cold Dark Matter model, LUCDM, is the most precisely tested cosmological model in history. It correctly predicts the distribution of galaxies on large scales, the temperature fluctuations in the cosmic microwave background, the accelerating expansion of the universe, the formation of galaxy clusters, and a vast array of other observables with extraordinary precision. The success of LUCDM is not a matter of modest confidence. It is among the most confirmed frameworks in all of science, and yet, within this extraordinarily successful framework, the submodels of galaxy formation, the specific physical processes that govern how gas turns into stars inside dark matter halos, have always been less precise, more parameterized, or sensitive to assumptions that the data could not previously test. Webb is now testing them, and the tests are returning results that are, if not yet breaking the model, at least bending it in ways that require either new physics or a substantially revised set of assumptions about the early universe. This is what I find most consequential about the JWST GSG-14-0 and MOMG-14 discoveries, not the records themselves. Records are broken regularly in astronomy, and each new farthest galaxy is eventually replaced by the next. What is consequential is the pattern they represent and the precision with which Webb is now measuring that pattern. We are not in a period of vague anomalies and hand-waving. We are in a period of precise, reproducible, peer-reviewed measurements that do not fit the existing picture, and that is exactly when, in the long, patient history of science, fundamental understanding tends to shift. There is a specific category of loneliness that belongs to light. The photons that arrived at the James Webb Space Telescope from MOMZ-14 set out on their journey 13.53 billion years ago in a universe that contained no planets, no complex chemistry, no possibility of life as we understand it. They crossed the expanding emptiness of space while galaxies formed and merged and evolved around them, while stars ignited and died and scattered their atoms into new generations, while the Milky Way assembled itself from a billion smaller collisions, while our Sun condensed from a cloud of gas and dust, while Earth cooled and froze and thawed and filled with water, and generated the first cells, and eventually, in what amounts to less than the last blink of cosmic time, produced a species that thought to build a golden mirrored telescope and launch it into the darkness to catch them. They were caught, and what they carried, encoded in their spectrum, was not merely a redshift, not merely a distance. What they carried was the news that the universe's very first chapter was stranger and richer and more violent than we had written it, that the first galaxies were already ancient by the time we would have called them young, that the atoms of oxygen and nitrogen that compose our own bodies were being forged, scattered and inherited in cycles of stellar birth and death before the Earth had even the faintest prospect of existing, that the oldest stars in our own galaxy, those dim, slow-burning relics orbiting the Milky Way in ancient clusters, may carry in their chemical compositions the direct memory of a galaxy smaller than a typical arm of the Milky Way, burning at the very dawn of everything 280 million years after the beginning of time. We are made of this history. Every atom heavier than helium in your body passed through at least one stellar core before it reached you. The oxygen you are breathing right now was forged inside a star that died before the solar system existed. And now, thanks to a telescope hanging in cold space 1.5 million kilometers from home, we can look back along the chain of inheritance all the way to its earliest links, to the first galaxies burning in the dark, setting in motion the 8 billion year sequence of stellar chemistry and gravitational architecture that would eventually result in you, here, thinking about this. What does it mean that those earliest galaxies do not fit our models? In one sense, it means exactly what Naidu said. It is challenging and it is exciting. In another sense, a deeper one, it means that the universe is more inventive than our mathematics. It means that, whenever we have built a complete picture of what happened at the dawn of time, the universe has found a way to complicate it with evidence. And this, I think, is not a failure of science. It is science in its most honest and most alive form. A conversation between human curiosity and cosmic reality, in which the universe always has something more to say. The question that MOMZ-14 leaves open is not a small one. It is not a gap to be filled by a better parameter in an existing simulation. It is a structural question about how quickly the universe was able to build complexity after its own beginning, about whether the processes we see governing star formation today operated differently, more efficiently, or violently in those first few 100 million years. It is a question about whether there exist classes of stars and classes of physical processes that have left no living representatives in the present-day universe and can only be glimpsed by looking back to the very beginning. It is a question about what the Milky Way's oldest survivors truly remember. We do not have the answer. We have the question, sharply defined, precisely measured, and more beautiful for its specificity. That, for now, is more than enough.